This is the second part of section 5.6, the elements of Galois theory. Now, in this video, we are going to just recollect this definition group of automorphisms of an extension field K of a field F, and this theorem, linear independence of automorphisms of K, and then definition of fixed field of G. This lemma, the fixed field of G is a subfield of K. And we are going to have the definition of automorphisms of K that leaves the elements of F fixed, which is denoted as GKF. And we will have this lemma in which we'll prove that GKF is a subgroup of G, and few illustrations also. So first we will have this theorem. Before that, just recollect the group of automorphisms of an extension field K of a field F. So an automorphism of a field K is a one-to-one mapping sigma of K onto itself such that sigma of A plus B is sigma of A plus sigma of B, and sigma of AB is sigma of A. This is actually the product which is defined in K, so sigma of A into sigma of B. Here also the same product in K. So one-to-one onto homomorphism from K to itself. So that is our automorphism. Now, in this theorem, which states that if K is a field and if sigma 1, etc., sigma n are distinct automorphisms of K, then it is impossible to find elements A1, etc., an not all 0 in K such that the linear combination is 0. So here, this is scalar 0. Here, we have two negatives. Two negatives makes the statement positive in the sense that it is impossible to find elements AI's not all 0. So here one negative, here one negative. So that means we should find elements A1, etc., AN all 0 in K such that this linear combination equals to 0. So that means it shows that see, this mapping is meaningless unless it acts on some element from K, because all the mappings are from K to itself. So that's the reason that it is given in this way. Now this in turn actually implies that sigma 1, sigma 2 and so on sigma n are linearly independent. The linear combination equal to 0 should imply each scalar 0 means the way whatever linear combination of vectors that you have considered, they will be linearly independent. So here we are having sigma 1, sigma 2 and so on sigma n. We want to show them linearly independent. So that is the meaning of this theorem. Now let, if possible, there exist scalars A1, etc., AN not all 0 in K such that the linear combination is 0 for all U in K. So what is given, we are writing in with the it is impossible, it is given, but what we are writing here is let if possible. That means we are considering the contrary of what is given. That means we have to arrive at a contradiction. So so what is assumed here? Let if possible. What we need to prove is it is impossible, right? So let if possible there exists scalars A1, etc., AN not all 0 such that the linear combination equals 0 for all U in K. K sigma i's are from K to itself. So naturally this U should be from K. Now among all such relations there exists one with fewest number of non-zero scalars. So what is the meaning of this? You see, such a statement you would have come across already when you proved your characteristic vectors are linearly independent in UG. That is maybe in section 6.2 in Hurston book, characteristic vectors. So they are linearly independent. Same concept is here, the same technique is used here. So among all such relations, see, we do not know. See, we have got the linear combination equals 0, in which we have said that not all 0. So how many of them are 0? We don't know. It may be the suffixes, I mean the automorphism suffixes say 1 to 5. 0 or 12570 or 12570. So among all such possible relations, there exists one with the fewest number of non-zero scalars. Okay, so definitely some of them 0, some of them non-zero. See, suppose up to 10 that I have, say, in which sigma 1 to sigma 10 I have. So that means I have a relation, say a1 sigma 1 u plus and so on plus a10 sigma 10 equals 0. So here we have to have with fewest number of non-zero scalars. So suppose I have sigma a1 0, a2 0 and a7 0, right? So a7 0, that means three scalars are 0 here. So how many are non-zero? There are 7 non-zero scalars. And suppose I do not know what relation that I will have. So in some cases I may have a1, a2, a7, a9, a okay, up to this. These are 0. So how many non-zero? 6. So in some case I may have a1 to a5 0. So in that case 5 will be non-zero scalar. So among all such possible relations, there exists one with fewest number of non-zero scalars. So that relation that we take, so I'll have a1. So this statement we are going to take as capital P. Now by suitably renumbering them, see we cannot have, so it is something like in your comb, you have a comb. So in this, some of the these things are missing, say, and you have a provision, say, that you can collect them, you can put them all. There is a slider over here and you can put them all in one side and you can use the same comb, say. So it is something like that. So we are suitably renaming them and calling that relation as relation 1, that is equation 1. So a1 sigma 1 u and so on am sigma m u equal to 0 for all u in k with m greater than 1. Why we stress that m should be greater than 1? If m equals 1, then we'll have a1 sigma 1 of u equals 0 for all u in k. So this vector is we have implying this is non-zero, we know. So above we'll have a1 to be 0, which is not true, as you have assumed that your a1 etc. an to be non-zero. So we have our m to be greater than 1. Now sigma i's are distinct automorphisms. There exists one C in K such that sigma 1 C is not equal to sigma m of C. There exists one C in K. The domain is K only for all the sigma i's. Now as 1 is true for all u in K. What is 1? This equation we have named as 1. So as 1 is true for all u in K, 1 is true for all Cu in K also. C we have introduced. So replacing u by Cu is what we get in this am sigma m. So here what we are going to do is we are going to use the fact that sigma i's are automorphism, means it's a homomorphism. Sigma i's are homomorphisms. So we will have sigma 1c, sigma 1u, a1 along with a1 plus a2 sigma 2c, sigma 2u and so on am sigma mc, sigma m of u equals 0. We shall name this as equation 3. This is our equation 2. Now we will multiply equation 1 by sigma 1 of c. So you are multiplying throughout by sigma 1c. Name that as 4. And already you have equation 3 in which the first term is a1 sigma 1c sigma 1u. So when you subtract, that term will go, and what remains is, see, when you consider you're multiplying equation 1 by this. So that is what you have as 4. So 3 minus, so these two only that we are considering. So this is 4 and this is 3, are subtracting. So this term will go. So that means from second term onwards we will have. So this is our second term, sigma 2 sigma 1 of C minus here the second term, this minus this. So sigma 2 C, what are common in both A2 and this? In both these two are common, so what remains is only this. So you have this term, and similarly and so on. The last one when we consider, it will be, this is AM. So you have AM sigma 1 of C minus sigma m of C whole thing multiplied by this equal to 0. Now for every u in K, you just for the sake of simplicity that we are taking this one as B to the whole lot. The whole lot here, just for the sake of simplicity, this is taken as B2 and so on. This is taken as BM. So B2 sigma 2 of u plus and so on BM sigma of u equals 0. And this is named as equation 5 for every u in K. Now in this, BM stands for what you have this, and here remember that this is non-zero, and by 2 these are, this one is also non-zero. So when your m is greater than 1, so you have your m strictly greater than 1. So what all scalars that you have in this relation, all of them are non-zero. And remember that this has got fewer coefficients than the number of coefficients that we have mentioned in this. So that means we are getting a contradiction. We have said already that with fewest number of non-zero scalars, and we are considering, we are getting a relation which has fewer non-zero scalars than what is mentioned earlier. So that's a contradiction. So that contradiction tells us, so since AM non-zero, sigma 1 C not equal to this, we have BM not equal to 0. Thus, in 5, we have m minus 1 non-zero scalars which contradict statement B. Hence, it is impossible. We said let if possible. So, it is impossible to find scalars not all 0 such that this linear combination is 0. So, this in turn tells that these are sigma 1 to sigma n. They are linearly independent. We have next the definition of fixed field of G. Let K be a field and G be the group of automorphisms of K. In G, naturally mappings are there, so composition of mappings that we are going to consider. And you define your Kg as all those scalars which are left fixed by all the automorphisms of K. So that's in words that you tell like that. Now the notation says Kg to be the set of all A in K such that sigma of A equals A for all sigma in G. So this is called fixed field of G. So we are going to prove that obviously it's a subset of K. We will say that it is non-zero, non-empty. The reason is 0 is an obvious element over here. So, and then we will prove that it is a subfield of K. This is contained in K. It's a subfield of K. So, for which it is enough we just check the criteria. Criterion, we will consider two subdivisions, one with regard to addition, the other one with regard to scalar multiplication, and non-empty is the usual process with which we start to have any subset to be a substructure of the given structure. So, lemma 5.6.1, the first lemma of the section, the fixed field of G is a subfield of K. You consider Kg, which is all those elements. So, whenever you are asked to see, if you have just mentioned, if they have just mentioned that the fixed field of G is a subfield of K, you are supposed to define what is meant by fixed field of G. So, that means whatever you are trying to prove, any subset to be a substructure, the description should be there. So, I used to keep saying that D and C is to be remembered. That is D for the definition or description. Whatever collection that you are going to consider as a subcollection of the given collection, what is that collection? That description should be there. That description should be there. And then you have to show that the description of the subcollection of the given structure. So that must be given, and non-empty, if at all it has elements only, we can further do anything with that. So it should be non-empty, and then the criterion for that to be subgroup or subfield, whatever it is. So in this case, two operation, field means two operation, one with respect to addition, the other one with respect to multiplication. So that means two conditions, one is a plus b and the inverse for any b inverse, meaning b minus b, and here ab A inverse. So clubbing these two and these two, it is enough you check whether A minus B is a member and A by B, or rather AB inverse, right? These two are in kg. This is what we are going to check. This is what we are going to check. So kg is to be first defined. So that is what is written here. And since 0, because homomorphism takes 0 element to 0 element, so we have this. So this is true, whatever may be the automorphism you have in G. So your 0 belongs to kg, and therefore kg is non-empty. Now we'll consider two elements A and B in kg. You need to show that A minus B is in kg and AB inverse also belongs to kg. So if any element is to be in kg, it has to undergo this test. That means sigma of A minus B should be equal to A minus B. So if it is true, then we can say that A minus B is a member of kg. So sigma of A minus B, because sigma is a homomorphism, you have this step. This is the reason, because sigma is a homomorphism. And because your A and B are in kg, you have sigma of A to be equal to A and sigma of B to be equal to B. So just substitute in the place of sigma of A and B here. So you are having sigma of A minus B to be equal to A minus B, and therefore your A minus B belongs to kg. And in the same way, if you consider this sigma of AB inverse, it's a homomorphism, so you have this step. And again, because it's a homomorphism, so this B inverse can be written as sigma of B the whole inverse, and this is nothing but A from here, and this is nothing but B from here. So A dot B inverse, you started with this and you are getting the same, means AB inverse should belong to kg. So hence kg is a subfield of K. So on description, you have to say that it is non-empty, and then the criterion for that to be a subgroup. So here two subdivisions, one is this with respect to addition, and the other one is with respect to multiplication. Next we have the definition of this GKF. Let K be a field, F be a subfield of K, then the group of automorphisms of K relative to F, that is how you has in names, relative to F written as GKF is defined as all those automorphisms which leaves the base field element fixed. So that is your GKF. So set of all sigma in G, all those automorphisms. In words, you must know how to read it. Those collection of all or the set of all. The set of all automorphisms of K which leaves the base field elements fixed. What is the base field here? It is F. Base field elements fixed. So that is your in terms of wordings, if we have to say, this is how you say. So here all mappings and there all scalars. Now we describe this fixed field of G there. Here the fixed field of GKF, that is given by all those scalars which are left fixed by all the automorphisms of GKF. If you have G here, for all sigma in G you will have. We have GKT for all sigma in GKT. So like that it goes. And throughout the section, only these two will come repeatedly. That is two concepts. One is about the scalars. So about the scalars which are all supplied from K, and the other one is group, that is mappings, group of mappings. So in here you have field of scalars, group and field. So we have K and G. Here in K we can have K, G, K, F and so on, and finally it has F, and here G, G, K, F, depending on what all sub collections, I mean subfields that you have. So this is fixed field, for that we are saying. Otherwise we will be saying that F is the base field, then you may have T, then you may have M, then you may have N, and then you have K. So corresponding to each one you can talk about GKF means GKF. For this you can talk about GKT, and for this you can talk about GKM, and for this you can talk about GKN and so on. So whenever you have subfields here, you can have correspondingly the subgroups in this collection. So that is what is going to happen throughout the section. What you must have a clear picture. I said already that whenever G, you start with G means what all there in that collection, automorphisms of K. Basically they are mappings. So whenever you have G, it is mapping. Mapping, you remember, then the notation will be G, GKF, GKT and so on. So mappings and scalars will be dominating the entire section. So now we are going to have the next lemma, that this GKF, see the fixed field is a subfield, section A, 2 marks question, and this one, that is GKF is a subgroup, can also be asked in section A for 2 marks, and even the definition of GKF or the fixed field of G, all that can be asked in section A. Right, now in this lemma we are going to have GKF to be a subgroup. So whatever subcollection that you want to show as a subgroup, describe it first. So GKF is all those, I said already, G means mappings. So when you look at the definition of KG, it will be all those scalars in K such that sigma of A equals A for all sigma in G for Kg. GKF means for all sigma in GKF. So here when you look at this, and this one, it may look the same. Okay, but here the importance is given to scalar, here the importance is given to mapping. So when mapping is here, scalars will be here. When scalars are here, mapping will be there. Mapping here, scalar here, scalar, so mapping will be here. So throughout the section, mappings and scalars will dominate, right? So here first we have to, this description we have got, non-empty we have to show, and then the condition. So you have identity mapping is the obvious element which will fix, which will take any element to itself. So it satisfies the criterion. It's an automorphism of K, and it fixes the elements of base field. So automatically it goes to GKF. So it's a member of GKF. Therefore GKF is a non-empty subset of G. And you consider two elements, sigma and tau, in GKF. We are going to prove that this is a subgroup, which means for every A comma B in H, A dot B inverse should belong to H. That is the criterion for H to be a subgroup. So that we are recalling, and so sigma composition tau inverse should belong to GKF. Now since sigma and tau are automorphisms of K, we know that composition is also one-to-one onto homomorphism, means it is an automorphism of K. So automorphism part we are not checking. we are only checking this one, this condition. So sigma composition tau inverse of alpha you consider by the definition of composition of mapping. This is how you write sigma of tau inverse of alpha, and sigma tau inverse no sigma will keep whatever element that you have inside the bracket. By its definition, it should leave the element as such, tau inverse of alpha, and this is tau inverse of alpha. But we know that tau of alpha equals alpha, which means it's a bijective mapping. So tau inverse can be applied on both sides. So that again gives alpha. So in that way also we can argue. First finish up this bracket so that you will have, in both ways you can argue. First you are applying, this means you will have tau inverse of alpha, and from here it is equal to alpha. But if you are going to finish off what is inside the bracket, then you will have this step, sigma of alpha, and sigma of alpha must be alpha because sigma is a member of GKF. So sigma composition tau inverse of alpha equals alpha means it satisfies the condition, and therefore it will belong to GKF. So GKF is a subgroup of G. Criterion checked, described, non-empty is shown, and condition checked. Therefore, GKF is a subgroup. So next we are going to have the illustration. See, this can be asked in section A again. Determine what is GKF if K is C and F is R. So like that also the question can be asked. Now we are giving illustration for GKF and KGKF. K is C, F is R. Consider the group of automorphisms of C. See, we know already that the automorphisms from Z to Z, you have only identity automorphism. And then from Q to Q, when you consider, again it is identity. And when you consider R to R, identity automorphism. Only one automorphism that you have, they are nothing but identity as far as Q, R are considered. But as for C is considered, when you consider automorphism, you have two categories. One is that can be identity automorphism, the other one can be conjugate. Usually we write like the sigma suffix, just I sigma suffix ID, and here sigma conjugate. So what is the meaning of it? Sigma is a mapping from C to C. All this we have already seen. Your sigma can take Z2, that is complex number 2 itself, or Z can be taken to Z conjugate. So this is your sigma suffix ID and this is sigma conjugate. So you have actually two automorphisms as for C is concerned. So here they are named as F and G. Here they are named as F and G. Now, so G consists of that. G consists of that. But in both the cases, G consists of automorphisms. What are the automorphisms? Sigma ID and sigma conjugate. So these are elements of G. But what is now needed is GKF, which means GCR. By the definition, all those automorphisms of G which leave the base field element fixed. See, this sigma, this identity transmission, identity automorphism, or this one, they don't change the elements of R. What they change is I only they change. I is taken as, I is changed as minus I as far this is concerned. So when you have A plus IB, only two possibilities. It goes to A plus IB or it goes to A minus IB. So which one changes? This I alone changes. So, but how about A and B? They are from R. Whether my sigma ID or sigma IC changes the elements A and B? No. So because they do not change, what are the mappings which do not change the base field elements? Both of them do not change the base field elements. So only you are getting instead of sigma id, sigma c, here it is taken as f and g, small f, small g. Okay, so the automorphisms f and g are respectively identity and complex conjugate automorphisms of C, which fix the elements of R. Now KGKF. So KG means mapping, finished. Now scalars. So by the definition, KGKF is all those scalars in K which are left fixed by all the elements of this. What are the elements available in this? You have only sigma id and sigma conjugate. What these two do? They do not change the as for the elements of R are concerned, they do not disturb them. They leave them as such. But when it sees the complex number, namely I, it will take it to minus I. So what are the elements which are left fixed by all the elements of GKF? They are only the real numbers. So you have KGKF, which do not memorize. See, students find this part very difficult just because they don't understand what is what. What is your K? What is your G? If you are thorough in that, because they only supply for the subfields or subgroups or whatever it is. So be thorough with what is K and what is G. K is a field, scalars, and G is mappings, automorphisms. So GK, when you consider, first you must know what are the automorphisms, and then only you can proceed. So this is the first one, and then next we have let f be q and k be q of cube root of 2. So in this what are the automorphisms? This we have already dealt in one of the problems in maybe in roots of polynomials. Yes, in the exercise problem somewhere 7 or 8 problems that we discussed, I suppose. So in there you have discussed if q of cube root of 2 is considered, the automorphisms are nothing but just the identity automorphisms. So that problem is to be referred. We are not going to establish that. It's already explained in one of the videos. So here my G itself consists of only one. So GKF we know to be a subgroup, even that should consist of only one mapping, namely identity mapping. Next, fixed field of GKF, all those what are the elements, what are the scalars which are left as such by all the elements, only identity. Identity element will take any element to itself. So whatever you have here, all that will come here. So here I can even have K. See, remember when you consider KGKF, all these elements should be from K only. They all should be from K only. So here in some cases you may have this to be K itself. In some cases it may be properly contained, and in some cases the whole of the base field. I mean the base field, whole of K are in between K and F. So in the first case we had the base field, and in this case we have the whole of K. So next is K is taken as f of omega, where omega is the one which satisfies this omega power 5 equals 1. Now you consider this omega power 5 minus 1 equal to 0. Taking omega minus 1 outside, this is what you have. Omega power 4 plus and so on. You have either this one implying omega to be 1 or this to be 0. So omega satisfies this 4th degree polynomial. This can be interpreted in this way. Obviously this is irreducible over Q. So you have F is your Q. The degree of f of omega over f is, if we know, see in the tower diagram, if we know what is the degree of the irreducible polynomial which this omega satisfies over f, that will be the degree of f of omega over f. degree of f of omega over f is nothing but degree of the polynomial. Here dimension, this degree stands for dimension, degree of the polynomial, irreducible polynomial rather, irreducible polynomial. So, so this says that f of omega is of dimension 4. So that means it will have basis elements consisting of say 1 omega, omega square, omega cube. F of a, when we consider, degree of f of a over f is n means what? How have we described this f of a? It is alpha naught plus alpha 1 a plus and so on, alpha n minus 1 a power n minus 1, where alpha i's are in f. So the same thing here, instead of in the place of a you have omega, in the place of n you have 4. So 1 omega, omega square, omega cube will be basis of this. We note that for any automorphism sigma of k, sigma of omega whole power 5, because sigma is homomorphism, sigma of omega 5 times you'll write, and based on the multiplicative rule, you have this to be sigma of omega power 5, omega power 5 being 1, you have sigma of 1, but it is 1 to 1 on 2, so it will take 1 to 1 only. So you have sigma of omega power 5 to be 1. So sigma of omega cannot be 1, because 1 is taken to 1, sigma is bijective. So you cannot have sigma of omega to be 1. So what are the possibilities for this? It can be omega, omega square, omega cube, or omega power 4. So these are the possibilities for once you have sigma of omega power 5 to be 1, these are the possibilities. Right. Now, you describe your k. This is a plus b omega plus c omega square plus d omega cube, where a, b, c, d are from capital Q, the field of rationals. Now, automorphism, we shall take them as say sigma 1, sigma 2, sigma 3, sigma 4, which are defined by, it takes 1 to 1, and it is described, see, based on the suffix you can have. Sigma 1 takes omega to omega. Once the image of this is known, for the rest we can easily write. And if you have sigma 2 of omega to be omega square, means sigma 2 omega square will be sigma 2 omega, which is omega power 4. So, and the same is sigma 2 of omega cube you can obtain, and that will involve omega power 4 into omega square. So that means, see, it is like this. You have sigma 1 omega to be omega. So how will you compute sigma 1 omega square? It is sigma 1 omega into omega, which is sigma 1 omega, sigma 1 omega. So it is sigma 1 of omega is omega. This is also omega. So it is omega squared. So like that, even here, when you consider sigma 2 of omega is omega square. So when you want to have sigma 2 of omega square, it is sigma 2 of omega into sigma 2 of omega. So that will be omega square into omega square. So that is written. And when you consider sigma 2 of omega cube, it will be omega square, omega square, omega square. So that is omega power 6, which can be written as omega power 5 into omega, but this is 1, so you get omega. So that is what we have written here. And for sigma 3 and sigma 4 also description is given. So G is this. Now we want to know what is GKF. GKF is all those automorphisms which leave the base field element fixed. It only changes omega, it doesn't change the elements of Q. So all the automorphisms, they leave the base field element fixed, which means GKF is G itself. And KGKF, when you compute all those scalars which are left fixed by all the elements of GKF. So it is only omega, if it comes, it changes. Omega square comes, it changes. Omega cube again changed. But what are the elements which are left fixed as such? It is the elements of Q. So that means what are the elements which are left as such by all the elements of sigma, all the elements of GKF? It is only Q. So GKF we have determined, and KGKF also we have determined. Now in the next video, which will be the part 3 of section 5.6, we will give example, one simple example, which will tell the relation between, or the correspondence between, the collection of subfields of K containing F and the subgroups of GKF. K is a field, so we can talk about subfields, and G is a group, so we can even GKF subgroup. So we can talk about the subgroups of them. So we'll try to establish by an example. Actual theorem that there exists a one-to-one correspondence theory comes later. Theory comes later. That's the main aim of the theorem. Main aim of the section. So that comes later. But here, just an example. So that will be very useful in understanding the some of the concepts that we are going to deal after this. So that part that we will do, and then theorem 5.6.2, whose statement is, if K is a finite extension of F, then GKF is a finite group. It's a group that we know. It's a finite group, and order of GKF is less than or equal to degree of K over F. See, once this is established, from here it is obvious that GKF has to be finite. So here you must know the general relationship between the number of elements and the degree is the number of elements in GKF is less than or equal to degree of K over F. So when can the equality be true? That is, order of GKF equals degree of degree of K over F. When it can happen? So all that in later videos that we will see. So this one we will see in the next video. Thank you.